Superb. So Krishna is joining us from the University of Texas at Austin in the US. Yep, we can see that. Perfect. Yeah, so in your own time, Krishna.
Great. Thank you, Kevin, for having me. Sorry I couldn't be there in person, but thanks for accommodating me online. So today we wanted to talk about doing differentiable simulations, but mainly with the objective of doing control with granular materials, that is manipulation of granular materials using autonomous agents. And when I mean agents, I'm talking about physical robots that interact with granular materials. So we're going to set the stage and put the problem to the very extreme. So we want to be able to control the soil in the lunar environment. So literally drive around the moon, push soil around, and be able to construct on it. It has its own challenges, even if we think about like excavation on Earth. You've seen these massive excavators, but in the moon's low gravity environment, where the gravity is only 1/6, these excavators need to be at least 6 times larger to create that same traction force to be able to dig. But unfortunately, we can't send like really massive equipments out there. So what we have to deal with is a restriction about 5 kilograms and be able to manipulate your granular material there. The other issue is the material property. Typically in geotechnical engineering, we normally say we have very few data points, but literally on the entire moon, we have one bore log that's drilled probably up to about 2 feet or 3 feet. So very limited data. Soil is extremely difficult because density is going to affect its behavior. So it could damage the wheels, it can get stuck in loose regolith. So how can I manipulate these materials without doing a lot of testing? And in fact, we are going to rely purely on perception to be able to manipulate these materials autonomously. So a part of this talk is going to be about autonomy and perception, and the other part is to be able to build these simulators and world models where we can train these robots. So going for what we want to do with these world models are where basically these robots get trained on. On the left-hand side, you have these RL-based simulators like Mujoko, which are low degrees of freedom, but extremely fast to simulate. They're efficient physics, but they are mainly limited to rigid body dynamics. And it can only do simple visuals. And somewhere in the middle, you have these Unreal engines, and you have these high fidelity visual data, but the physics approximations are often unrealistic. On the right-hand side, you have DEM simulators like Chrono, developed in University of Wisconsin, for Standard Group, and Group, where they're doing like high fidelity, accurate DEM simulations on like lunar surfaces. So we've seen a lot of these world models. So I've shown you a variety of those fidelities, but we can also ask LLMs, or in this case, like AI models, which can generate video about what it would look like excavating on the moon. This is Google's Genie 3, but our goal is very fast world models where our robots can train. So one of the argument is like, why don't we ask a language model, a vision or video-based language model to generate these? I'm not sure if audio came across, but one of the things, it was doing, let me go back, is if you look at the simulation, it was also generating some sound while it was dragging the scoop backwards, and the soil magically kind of hops onto the scoop, which is very nice. If our real world works like this, where we drag the scoop backwards and the soil jumps onto the scoop, that would be wonderful for excavation problems. But what if we use these as a really good first pass, in a sense, like, can we go from these world models, which are generated purely from perception, video alone, make it interactive, make it physically correct, so that the robots can learn something better and be able to simulate it. So on the other end is like these high fidelity discrete element simulations, which are done for robots to navigate complex environments. You can see like the track it leaves getting stuck. And what we want to do is, as it navigates this complex environment, we want it to be able to figure out when to lock its wheels, when to go over a particular obstacle, and when to drive around particular bits of rock. And can we do this really fast? Because you have a 4-second delay between communicating between the Earth and the Moon. So you need to be fast enough to make decisions. It needs to be fully autonomous, so we can't offload it to the Earth to do all the computations. So how can we build really fast surrogate models which are reasonably accurate? I don't want 100% accuracy like a full DEM simulation, because we're going to run thousands of these DEM simulations at every point to be able to make a decision. So this is where my journey for looking for a surrogate model started, and started looking at mainly like material point method type simulations, which is a continuum based approach, which allows us to do really high fidelity simulations of, like in this case, it's like dam break going through 5 barriers. That takes about 3 hours in terms of inference time. But on the right-hand side is the graph neural network-based surrogate, which only takes about 5 seconds to run. And always the biggest missing piece, and Kevin mentioned to purposefully highlight that, is what is the training time? Of course, the inference time is only like few seconds to run through this, but the training time is always the killer, which is, in this case, it used to be about 2 weeks. For most of our 2D simulations can be done in a week. Can be done in 2 days. This one, if you're training it on a single GPU, will take about a week to run. But the good thing about graph neural network is its ability to do generalize beyond the geometry in which it is trained. In fact, it was never seen a geometry with 5 obstacles, and it's able to do that reasonably well. And the reason is instead of just using purely perceptron alone, a perceptron is basically a linear combinations of your basis functions and your weights and your input functions, and then put it through a nonlinear activation function. But unfortunately, this means the order matters quite a lot when we are dealing with multi-layer perceptrons. So even if I have 3 balls, every time I have to rearrange the balls, it means I have to redo a lot of simulations and generate a huge amount of training data. What we are going to do with graph neural network is that instead of using MLP as a standalone for the entire system, we are going to use multi-layer perceptrons locally, by which we mean like we're going to take our domain, and then we are going to use the multi-layer perceptrons at the nodes and edges, so representing particles and the interactions as separate MLPs, so we can learn what is happening. By representing the system as a graph and trying to learn what's happening at a local level, we basically allows us to be permutation invariant, which means we only need like few simulations. In fact, we can run with just 10 simulations or even fewer simulations of DEM or MPM, where we learn the particle interaction or learn the constitutive law by just through like few 10 simulations. So how does it work? We start with an entire domain where we have this domain represented by a system, and we break down that system into individual particles. In this case, where we have individual particles are represented by nodes in this graph, and the interactions are going to be represented by edges. And our goal is to figure out how does this graph evolve through time. And we have 3 parts. One is the encoder, which goes from the physical system to a graph-based system. And we are going to have a processor stage or message passing stage where we are going to evolve the graph from the current time step to the next time step. The important thing to remember in the processor is the graph structure does not change. So as I go from time step T to time step T plus 1, the graph structure remains the same. But I get the updated features, and when I go to this time step t+1, where the dynamics is actually decoded, this is where the graph structure changes. So the main processing step, the graph structure remains completely intact. And I wanted to mention that if you want to try out any of our graph neural networks or other codes, they're available here on the GeoElements repository. So the first part is the encoder. Here, we're going to represent the physical state of the system as a graph. So take out the positions of the particles, or it could be positions of the material points, where we represent particle position, mass, its history as represented in the nodes. We only use spatial relationships. So we are looking at what is the a distance between the two nodes rather than specifying exactly what position it is located. And the message passing stage is where we are going to update our graph features. So we want to go from a node, which has its own MLP, the edge, which has its another own MLP, and there is also a global MLP, which represents the global state of the system. Our goal with graph neural networks message passing is basically to evolve the system or learn how to interact between the nodes and basically update these vertex and edge features at each of those positions. So the first step is to construct a message, and we are going to construct a message by defining which one's a source node, which one's a receiver node. We use a neural network to get the features from the source and receiver nodes, as well as global features if needed. Put that through a neural network so you get a fixed dimensional latent space message. And typically that's about 128 dimensions. Once we have messages along these edges, which is edges from going from node I to node J, we can basically do a summation, but we can also conserve momentum by making sure that the latent space messages are opposite of each other. And then once we have all these edge messages, we basically do a superposition. So literally sum over all the edges that are connected to the node and use that aggregated edge features and the current nodal feature to then push it through a neural network again to get the updated vertex feature. So that's it. That's the fundamental building block of a graph neural network is first construct a message, aggregate the messages over all the edges, and then push it through a neural network for the vertex to get an updated vertex information. So once we have this updated vertex information, we want to be able to update the physical one. Remember, the graph itself is a latent representation. So we want to go from the latent world to the physical world. Normally, it is done through just passing the current position and velocity and update the next position. But it means you're forcing the neural network to learn multiple things, like understanding the system. But what we can do is improve on this prediction. So rather than saying predict the next position, we can say the next position is going to be pretty close to where you're currently at. So you're only learning the error in the position. Or if you know the system dynamics even better, like I know an inertial prior, then all I need to know is predict the acceleration term, and I can use a semi-implicit time marching scheme to predict where the next position is going to be. So this means once I have the acceleration, I can basically decode using a neural network to go from the latent space vertex features to a physical value, multiplied by dt to get velocity, multiply again by dt to get position. So you're integrating it through time and be able to learn the system. So we do have a distributed data parallel GNS version currently, which scales pretty well. In this case, you're basically dividing up your training data into embarrassingly parallel sections, split it up across multiple GPUs, and allow it to train. This allows you to improve the throughput of the system and be able to train a large geometry, but you're going to be still limited by the maximum number of particles that you can train. I'm going to list some of the limitations of GNS towards the end of the talk. But what this allows is cut down our training time, which used to be about 2 to 3 weeks, to just 3 days now on A100 machines. This is still a single node, multiple A100. So we had 3 A100 to up to 12 A100. So this is going across 4 nodes in this case. So what this allows us to do is, because the graph neural networks learns the local interactions, you can basically do high fidelity DEM simulations or high fidelity NPM simulations on small scale problems, and then scale it up to be really large, where you can have extremely large scale systems, and we've done it up to 20 times bigger than the domain that we have trained it on. And the simulation domain here, you can see the NPM, which is 8 times larger than the original training data set, and the GNS is able to replicate that mechanics reasonably well. So the big limitation would be number of particles. If you want to do a huge number of GNS simulations, the current limitation is on a single node, you could fit up to 500,000 GNS particles, each connecting to about 6 nodes. But the generalizability of GNS is what makes it very special. Even if you have only about 10 simulation data, you could train your GNS, and because it learns the local interactions, in this case, it learned the local interactions on a single barrier, it is learning how a single node is going to interact with the barrier node through the message passing aspect. We can basically change the geometry relatively easily and be able to predict the dynamics for a completely new system. And as long as there's enough of the velocity distributions in different directions, then you're able to even change the geometries completely. So I want to show the generalizability benefit in terms of material property. So in all these cases, we only train the graph neural network for a single geometry, which is aspect ratio 1. So in this column collapse, the height to the length ratio was only 1. And we were trying to predict what is the behavior would be for different aspect ratios. And we trained it on 3 different friction angles. So you can see here, we trained it on 21, 30, and 40 degrees, and be able to predict on different geometries, but only on one, trained only on a single geometry. And it's able to replicate the actual NPM simulations really well. But it does take time. So what if you did not train across a range of friction angles? So for example, on the top row, I have within the data distribution. So my test data or unknown data set is inside my training distribution. You can look at the solid line here. My prediction looks exactly right. But once I move it to a system where it is out of distribution, where either the friction angle is different, or I'm trying purely cohesive material, because the entire GNS model has never seen a cohesive material. It has only seen friction, or it has probably only seen one friction angle. Then the out of distribution material is not very good. So how do we adapt graph neural networks to completely new data sets without having to retrain the whole thing from scratch? One possibility is to do like fine tuning, like you would do in an LLM, like take a really large language model or AI model that is trained on a large amount of data, fine tune it for your specific instance. So we tried doing it. So we try to compare pre-trained model and then look at the error within data distribution and outside. And you can see that the pre-trained model within data distribution is only lower, but as you go outside to 20 degrees or 40 degrees, it's completely predicting incorrect results. Whereas if you fine-tune the entire model, this again takes about a day or 2 days to do, depending on how much data you have. Then the error goes down quite significantly, and it is able to reproduce the dynamics reasonably well. But what we did notice was rather than training the entire model, which has 10 message passing layer, we only had to fine tune the first 2 layers of message passing to be able to capture the new dynamics. So we started with this idea, and rather than doing an entire fine tuning, we proposed the approach of what's called as a film adaptation. In this case, we had trained a graph neural network model, but it did not have friction angle as the input, in which case I only trained it on a single friction angle. It took me like a week to train this model, but now I wanted to adapt it to a new friction angle, or even incorporate cohesion into my system. So rather than doing a fine tuning, which is not possible because in this case I didn't have input of friction or cohesion in my model, we use what is called as a film adaptation. Film is basically taking your MLP's latent space and doing a fine transformation to the latent space. So I'm going to incorporate my friction and cohesion, pass it through a small MLP, and only learn how to modify my hidden layers or messages doing an affine transformation, so that it basically adapts my graph neural networks into a simple, into new material properties. So what this allowed us to do was to introduce cohesion into our model, where the model did not even have friction as an input. And you can see that the film's adaptation is pretty close to the ground truth. And if you look at interpolation and extrapolation, and we can see that our models for film and model, which is fine-tuned, and when I mean fine-tuned, it is fine-tuned for that particular case, we are getting pretty close to the actual result. And the film adaptation for OOD is really good because we can just take 5 different data sets of cohesion or new friction angle and rapidly adapt. And it is reasonably rapid, and in terms of the whole adaptation only takes about 20 minutes to train, whereas fine-tuning your model would mean you're only fine-tuning it for a given cohesion. Film allows you to do an extrapolation or even like a range of distribution of data in one 20-minute rapid adaptation. So we've taken this approach, and we have also tried to accelerate other numerical methods or combine it with other numerical methods. So in this case, we were interweaving between NPM and graph neural networks, where we run a few NPM steps, and when we think it's okay to run graph neural network steps to have like rapid forward predictions, and the error starts to diverge. If you're doing a PDE, you basically get a residual, but in this case, we do it at a fixed time update rather than looking at a residual to see how quickly I need to adapt. And when you're doing a really large scale simulations, you have to distribute your domain. So there are certain regions which are local only to the GNS area, and certain regions which are done by NPM, which are our high fidelity regions. And we've been able to push the NPM simulations up to like 12,000 cores on Frontera GPUs. And we use like dynamic graph partitioning that allows us to do these really massive 50 million, I thought I had a video, really massive 50 million material point rendering with GNS doing like the coarse region, NPM doing the fine region, and we are also doing in-situ rendering. It's the idea that you're basically simulating and visualizing your actual render at the same time. So 8 nodes are basically doing the real-time rendering, whereas 16 nodes are doing the actual computation, and we shunt the data directly across memory without writing it to a disk. And here's the recording of that in-situ visualization, which we did. This is 50 million material points, and it takes combines both NPM and GNS, and you could see a little bit of lag here where we were changing the frame rates, and multiple universities or locations can connect to it, do their own visualization without affecting other person's results. Sorry, I got out of the slideshow. Let me go back and so far I've been talking about forward simulation, but if you want to do control, our goal is to do inverse. So I want to achieve a particular target. How am I going to control my input properties, whether it's the material property inference or the control policies that I have to be able to achieve that result? So for that, what we normally do is use a inverse method or optimizer. So the first step I need is to know what is the gradient of my result with respect to my input control parameters. Once I have the gradient, I'll be able to use a gradient-based optimizer to update it. You can also use like non-gradient based approaches, but we are going to think purely about gradient based methods here. So in this case, we can do finite difference, but finite difference is going to need like 2 simulations at each run, and the gradients are usually not very accurate. This is where differentiable programming comes in, where we take the idea of a neural network learning and updating its weights through automatic differentiation and be able to apply it to our own traditional solvers as well as graph neural networks. So what we're going to do is use something called automatic differentiation. It is the idea of writing out your computation in a directed acyclic graph. So for example, if I want to solve x1 squared plus x2, I write it out as a graph and do a forward pass where x1 is 2, x2 is 3, square it, add them together, you get the result. This is just setting up the graph. The back propagation is where the interesting part happens, is the reverse mode automatic differentiation, where we compute the gradient of each of the node with respect to the previous one. And this can be pre-computed and ready to go. So when we actually have the values x1 and x3, we can just apply a chain rule going from the result back to the input and get the exact gradient. I do mean here the exact gradient, whereas if you did finite difference, this won't be exactly 4 and 1. Here we do get exact gradients through our simulation. This is a very simple graph doing x1 squared plus x2. But if you do like really complex models, then this graph can get completely difficult and extremely large as well. So going back to our lunar digital twin, the goal that was set to us from NASA was, can we use purely perception alone to be able to identify what is the material property? So we're going to use a single scoop of material and then pour it or look at the dynamics of what's happening. And all NASA has in this situation are 2 stereo cameras, which can point to any location, and they want to observe the dynamics to infer material properties. Because hardware cannot be changed, we are limited by what we are offered here. So we started off by looking at neural radiance field, where we have multiple cameras taking pictures. Usually NERF takes about 11 to 30 pictures of the scene to be able to accurately represent a 3D model. The way NERF works is basically construct or overfit a multi-layer perceptron, which represents the 3D object. So that can minimize the loss as we look at camera angles from different views. So our goal is to figure out, if I have multi-view camera angles, what is the object that generates this camera views or pictures. And we take that objective and see if I push through sand and purely take pictures of what is happening to the dynamics, can I recover back what is the underlying material properties? This is again an MPM simulation, which we are looking at, and we are taking pictures at 11 different camera views and record the dynamics, and we want to infer what is the friction angle in this case. We're going to use MPM, but in this case, we'll be using a fully differentiable MPM, which means I have a big computational graph, and this is like a single cell in the NPM simulations, and I have like thousands of it, so about like 5 million graph nodes that I need to differentiate through. So the goal is we capture the visual data from multiple angles, create the model, or what we think is the 3D model, and then we can take that 3D model and convert it into material points. And once we have that, we can take pictures at those specific locations and try to minimize the dynamics or the pictures that we see. And we do it at different time steps and eventually get the loss with respect to all the time steps, and then back propagate so we can figure out what is the actual material property. And we can also do it purely as an image loss. So we were starting out with a true value of 45-degree friction angle and see how we converge to that value. Or even if you just had a video, you can even estimate what are the properties or forces in the system. But this method is better because we are using automatic differentiation rather than finite difference, which means my gradients are way more accurate. It is computationally heavy to do, and I have to do like gradient-based checkpointing and other methods to backpropagate through the entire simulation. But you can see that the loss landscape is much better captured by AD than doing purely a finite difference type system. So this gradient-based material point method simulators or gradient-based differentiable simulators allow us to do a new type of problem. Usually in robotics, if you're doing like model-based control, you need a huge number of simulations, and we're talking about thousands of runs at each time step. Whereas if you're using a differentiable simulation, we can basically learn something called a differentiable predictor control. Because it uses the gradient information, it's able to learn a lot more quickly and be able to control our system even better. So we've been using DPC to do excavation. So there is a trained policy in this case where we are comparing it with AD and a Bayesian approach. And if you look at the red dot at the bottom of the screen on the left, you can see that we're going to keep moving that, and the wheel learns how quickly to accelerate, what is its position, and it is also changing the environment as it is navigating that system. So it needs to have an updated view of the environment, of what is happening in that environment as the system dynamics changes, and the environment in which it is operating is also continuously changing. But the benefit is because we have the gradients in all our simulations, we can backpropagate through all of those, backpropagate through our policy, and have an offline trained policy which we can directly adapt and be able to predict what should happen on board. The other thing you could do easily is estimating forces from videos. So because you have a fully differentiable simulation and you're comparing a loss based only on perception or images, we can do that iteratively and see how we can capture what are the forces that are acting on the wheels or acting on the flow in that case. So the last part I wanted to highlight is the going from nerve-based simulations to something called Gaussian splats. Where Gaussian splats basically allow us to do a very quick 3D generation, whereas instead of using a neural network, we're basically going to use 3D Gaussian blobs. So think of your Gaussian distribution, but in terms of 3D, so it's going to look like a blob, exactly like a ellipsoidal thing. And whenever you're generating an image, you're basically like splatting it into a 2D frame that gets us the image. So what does a splat have? It has a position. It has a shape defined by the covariance, that's the ellipsoid. You can add color and spherical harmonics, which allows you to do a view-dependent color. And then you can also add opacity to it, which means we can take multiple images or camera poses. In this case, we need way fewer than what Nerve needed. So we can get away doing like 4 or 5 multi-view cameras. And then use structure from motion to initialize these tiny blobs. In this case, we need 200,000 blobs to represent the plant. And once we have the plant, you differentiably render it to look at the original images against these rendered images. And that allows us to keep iterating until we are able to get a 3D representation of the plant exactly. But now that each of these plant is represented by a blob, which is like a material point, or it could be like a DEM, you can assign material properties to it and make it behave like a realistic object. So remember the world model which Genie generated? All I need now is like use that as a base model, take multiple views, and now I have a physics-based simulation rendered very quickly. Sorry, I don't know what happened here. Okay. So going back again. All right. So when we apply material properties, you can see that the individual blobs now behave like material. So I can assume the entire plant is made out of sand, or it could be a viscoelastic plant with an elastic pod, and I can get a physical representation of the system directly from pictures. What this allows us to do is take regional scale footage of construction sites or even our lunar environment. This is a 10-second clip of a 1-hour video of a drone footage and be able to render a regional scale Gaussian splat with about 5 million material points. This takes about 8 seconds to render. The initial construction takes about 30 minutes, but once you have 30 minutes, it takes like 8 seconds to render the entire simulation, entire scene. But the good thing is we can actually assign material property to our entire scene and go from real videos to a fully modelable system, which means I can now figure out how to drive around these systems when it rains, what type of wheels to use, and be able to drive a truck through it. This is not a video, but like based on the environment, we have generated this simulated system where we can literally drive a truck through our Gaussian splat and see how that system is going to define. And this is done using NPM, and we are trying to accelerate it by doing it in the latent space using graph neural network. And this is us throwing the plant against a wall where the graph neural network is able to represent the dynamics of what is happening to the plant. And all of this is to figure out how do we go from videos and quickly generate a simulated world that looks very close to the real world. A big gap in robotics is how to close the sim to real. So we are going to start from the real world, create a simulated world which is exactly identical, and then be able to train the robot in this created or simulated world using something called MPPI. Model-based predictive control is basically generating thousands of trajectories and doing a weighted average of those trajectories to be able to predict what the next position will be. And here is where GNS will be useful. So remember having to do like 1,000 DEM simulations in a fraction of a second. A surrogate model becomes extremely useful. And because we're going to do a weighted average, the errors are not going to blow. Errors are not that critical. So if you're about 95, 97% accurate, we're reasonably good. So the first step on the left-hand side is the real-world video of an excavator that we have. Is able to identify the material property. On the right-hand side is the simulated environment. So I want to highlight the right-hand side of the simulated environment with Gaussian splats and the right material properties using NPM. So we are able to train the robot and be able to autonomously excavate using MPPI. So here is our offline trained robot. Which is able to excavate to a prescribed depth, and it is also going to level out the ground. I do have this video not accelerated in a sense, it's operating in real time, but each of those steps, it stops for about 30 seconds, thinks about what it needs to do. And when I mean thinking about what it is trying to do, it's basically running thousands of GNS trajectories forward, then pick out the best averaged out trajectory to get the result. So it opens up, these surrogate models actually open up a new world of possibilities of differentiable simulations, either for optimization or even control type objectives. But wanted to highlight at the last, like, what are the benefits and challenges of using these surrogates. GNS is great because it's very good at adaptation to different material properties and geometries because it learns local interactions. It's really fast. It's fully differentiable. It needs a few simulations, only 10 if you have like a single material, 100 if you want to do like a multi-material simulation across a range of parameters. It can also be rapidly adapted to film, but it does have its own challenges. Typically, GNS requires warm starting, which means I need 5 previous time steps before I can predict forward. Once I have the first prediction, you can auto-regress, but your 5 previous time step means you're limited to doing the initial few steps in NPM or a approximate solver. The maximum number of particles is still limited unless you can do a distributed GNS using sharding, which we currently have, but I'll tell you the issue in a moment. So the maximum number of particles we can push realistically is about 500,000. Because of differentiability, we are going to be much more limited if you want to get a fully differentiable GNS. For just a forward GNS, you can go up to 500,000 particles. Distributed training becomes an issue because we randomly sample 5 or 6 time steps and then train the GNS over 2 million steps. And at each time, you might get different training data, which means we have to pre-write or predefine how we are going to shard the graph at each of those time steps and write it to a disk, which is going to be an enormous time sink. But this can be done because it's a pre-processing step to a training process that allows us to actually divide up the graph, so we are no longer limited to 500,000 particles. But this is a big challenge in GNS as we try to scale it and still retain the accuracy of this system. All right, I think I'm about time, and thank you so much for having me, and happy to answer any questions.
Krishna. So we have some time for questions. I'm sort of slightly rude here because I realize that we can see you, but you can't see us. So there's between 30 and 35 people in the room who you can't see, who have been hanging on your every word, and who I hope will come up with a good question. So questions for Krishna? Yes, Carson.
Yeah, thanks for this amazing talk. Very interesting. If you now changing the particle properties, the morphologic characteristics, the size, adhesion, and in a more extreme manner, does it mean you can also work with this adhesive layer on top via retraining your graphical neural network, or do you need something more?
Yeah, I think what we discovered was when we were training only for adaptation to different friction angles, we had to only change the first layer of message passing. Depending on other properties like cohesion, needed changing a lot more of the message passing layers. So we had to change up to 5 message passing layers through film adaptation. But film is still a fine transformation, so it's still linear plus some shift. So I think I don't want to say we can capture all the dynamics because at the end we're still only doing a linear transformation of the latent space. So there are distribution ranges that we capture and then see how much we can adapt. So it would depend. We don't yet know how many layers to change and how far the linear adaptation works with respect to different properties. But I would say for friction and cohesion alone, changing the first 2 or first 5, and it's a 20-minute adaptation. Now you can run a range of cohesion and friction angles as its strength, and other properties needs to be studied a lot more.
Thanks.
Other questions for Krishna?
Hopefully you can hear me. I have a question on the way the graph is set up. So you have your nodes and edges, and you said you're only tracking the sort of relative position of the particles. I guess this works really well with spheres. What I'm just wondering about is if your training data was based on a multi-sphere particle and you have particles separated at different distances, you know where they are, but you don't necessarily have any information on, say, the orientation of the particles and maybe what the contact separation was. Does that mean you need additional training information in the graph, or do you have to include more edge data or node data? How does it work that way?
So in my case, I'm trying to predict the bulk dynamics of the system. So I'm using a multi-stage message passing. So even if in DEM, like we're only looking at the nearest neighbors or particles which are in contact with our system, we can, in my case, with the multi-stage message passing, you're passing the information across multiple particles, and so it learns the global dynamics. If you want to do like different shapes, the typical bottleneck is, aside from like finding out what your contacts are, is the computation of the constitutive law, the contact force itself. Rather than doing a multi-stage message passing, you can replace what's called an interaction network, which is basically a pairwise network. So you retain all the DEM, but learn the interaction between multiple shapes. how you want to encode the shapes could be different. It could be like you can use a function to represent the shape into a latent space, or you could use like convolutional neural network in 3D to represent into a latent space. Use that as a feature to figure out how many contacts, in which case you don't have to, you probably can get away doing 3 or 5 DEM simulations because you have like lots and lots of contacts of different orientations. Or you could literally just have your different shaped particles interact at different angles without having to do a full-blown triaxial compression, for example. That kind of operator learning would allow you to accelerate where you don't have to worry about the shapes and the orientation, which are still captured by DEM, still retained by DEM. You can use quaternions and others to keep the orientations, and just replace the constitutive law with an interaction network.
Related to the lunar regolith material, if I have it correct in mind, I think it ranges from several microns to several hundred of microns, this fine material with a medium or average value of 50 microns roundabout. I don't know exactly anymore. But that means at the end, if you have maybe 1 billion particles per cubic centimeter later on within your real simulation, does it mean that the material point method is the way to go instead of the DEM?
Yeah, in our case, we use NPM because I'm interested in figuring out how to move the bulk of the material autonomously and reasonably quickly. So having this continuum-based approach actually helps. And the approximations that we do with GNS is also valid within this environment, because at the end, I want to know where exactly to place the plow and how much to push the plow forward, rather than understanding precisely where exactly each particle is going. I want to roughly estimate what is the distribution of the particle and where they will flow, rather than precisely estimating where individual grains are going to end up. So depending on the dynamics and the approximations you can live with, I think we have to pick different approaches in those cases. But to do autonomous robots, and like the ones we had, we are also trying to drive on ice, literally like drift on ice. And in those cases, we are driving a remote controlled car at 50 miles an hour. And I need to be able to do 500 simulations in microseconds. So GNS and continuum-based approaches are the only way to go at that scale, probably right now.
Fantastic. Thank you very much for that, Krishna. That was wonderful.